In this presentation, we're going to outline two different ways to find the frequency response of a linear time invariant system. The first will be using MATLAB, and it's quite easy to find the frequency response with this software package. So let me just give an example to show you how you can do it. Our example is g of s is 10s plus 20 divided by s squared plus 7s plus 100. And our first step is going to be defining the system, and we'll define it by giving the numerator and denominator polynomials as arrays of coefficients. So I write num equals 10, 20, and that defines the numerator polynomial by giving the first and 0th order coefficients of that polynomial. Then, in a similar fashion, I find the denominator polynomial. Den equals 1, 7, 100. And then I define the transfer function as the ratio of those two. G equals TF num den. So we've defined the system with those first three commands. And now to get the frequency response plot, I type Bode and then the name of the transfer function I'm interested in this case, G. This will plot both the magnitude and the phase plots versus frequency, the frequency in radians per second. The magnitude will be in dB here. The phase, of course, will be in degrees. So you can see it's quite easy to find the frequency response using MATLAB. Now let's suppose you really don't like to use dB for your magnitude plot, and instead you want to have the gain plotted just as the gain. So then what you do is the following. We have to set some plot options for Bode. And the first lines here do this. We say P equals Bode options. Then we say P.magscale equals log. That will convert from dB to log. And then P.magscale units equals absolute, ABS. And then we type Bode G comma P. That will give the magnitude plot in terms of gain and not in terms of dB. Now when you type Bode, it will automatically pick which frequencies that it will draw the magnitude and phase plots for. But if you want to use your own frequencies or some particular frequency range of interest to you, or you want to have more points around some particular frequency of interest, you can define your own frequencies. Now the easiest way to do this is to use the log space command, and so here I've got an example. W equals log space minus 2, 4, 1000. And what that does is it sets up 1,000 points evenly spaced on a logarithmic scale between 10 to the minus 2 and 10 to the 4. That is between 0.01 radians per second and 10,000 radians per second. Once we define this array of frequency points, we then just have to include it the Bode command. So we wrote Bode G comma W. Now there's lots of other Bode options beside the ones I've outlined here, so you can just see the MATLAB help to learn more about those. Let's suppose someone's given you a Bode plot and you want to convert it from dB to gain. How do you do this? The first step is to divide the dB by 20. So 20 becomes 1, 0 becomes 0, minus 20 becomes minus 1, and minus 40 becomes minus 2. The next step is to raise 10 to each of these powers. So we have 10 to the 1, 10 to the 0, 10 to the minus 1, and 10 to the minus 2. These numbers are then the corresponding gains. So 10 to the 1 becomes 10, 10 to the 0 becomes 1, 10 to the minus 1 becomes 0.1, and so on. Now you've converted dB to gain. So now you know how to find the frequency response plots using MATLAB. We'll now look at sketching these by hand. And the value of this method is that this will give you insight into the relationship between poles and zeros and the shape of the frequency response. So here are the rules, and there'll be 7 of them, for sketching the magnitude plot. In the first rule, we'll find an integer m, and this integer will dictate the slope of the magnitude plot at low frequency. So m is equal to the number of zeros of the transfer function at the origin minus the number of poles of the transfer function at the origin. Our second step is we'll remove any poles or zeros that are at the origin to find a new transfer function, which we'll call h of s. Then we'll find a scalar value, which is the DC gain of this new transfer function. We'll label that h0. Now we'll plot a point at 1 radian per second at the absolute value of this number h0. h0 could be either positive or negative, and when we take the absolute value, we'll get a positive number, and we'll plot this at 1 radian per second on our log-log scale. In the third step, we'll draw a line through the point we just plotted with a slope of m decade per decade. So here we're using this integer value we found in the first step to determine the slope of this asymptotic line, which will go through the point we found in step 2. In step 4, we'll find the poles and zeros of the transfer function h of s. Note this is the poles and zeros of the new transfer function, the one that already had the poles and zeros at the origin removed. So we find the poles and zeros of this new transfer function, and we find their magnitude. Their magnitude is how far they are away from the origin. Then we'll order the poles and zeros by this frequency magnitude. In step 5, we'll move from low frequency to high frequency, and we'll adjust the slope of the line that we established in step 3 at each frequency magnitude by the following rule. For each pole, we'll decrease the slope by 1, and for each zero, we'll increase the slope by 1. So we move from low frequency to high frequency, adjusting the line every time we come to a pole or zero frequency magnitude. And this is why it's important to have them ordered from low frequency to high frequency, is because we'll successively adjust the slope of the line. When we finish that process, moving from low frequency to high frequency, and we've adjusted the line for each pole or zero we encounter in frequency, moving from high to low, we've completed that process, we've constructed the asymptotic curve. And that is step 6. Now the asymptotic curve that we've constructed in steps 1 through 6 is not accurate near the frequencies of the poles and zeros. And so in step 7 we try to adjust the curves we found, smooth them out, so as to account for the effects near the poles and zeros. For any poles or zeros on the real axis, the effect that will appear is a change in slope. And what we'll do is we'll smooth these corners, cut the corners down. For any poles or zeros that are close to the imaginary axis, we'll get a rapid change in gain near there. For poles, there'll be a peak of gain, and we can figure out the peak of this gain using m sub r and omega sub r that we discussed earlier when we looked at second order systems. For any zeros, the effect will be exactly opposite. We'll have a drop in gain for zeros that are near the imaginary axis. Now it's important to recognize here in step 7 that you'll never get perfectly accurate plots, especially near the frequencies of poles and zeros, and especially poles and zeros near the imaginary axis. But it's probably better to do some adjustment than to completely ignore the issue of what happens near the frequencies of the poles and zeros. If you really want very accurate curves near the frequencies of poles and zeros, well, you can always go back and do the plots on MATLAB. We've now completely outlined the procedure for sketching frequency response plots. In our next lecture, we'll look at many examples to illustrate the technique.